The fundamental property relations are the total differential expressions of the following four thermodynamic potentials. They are internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. So now let's write down the total differential expressions for these four thermodynamic potentials. So for internal energy, it is going to be du is equal to temperature TdS minus PdV. For enthalpy, it is TdS plus VdP. For Helmholtz free energy, it is dA is equal to minus SdT minus PdV. For Gibbs free energy, it is dG is equal to minus SdT minus plus VdP. And these equations are called fundamental properties because they are derived from the first law of thermodynamics. They represent the energy balance of closed systems, and they are the fundamental for other important derivations such as Maxwell's equations. So the need for these equations are we can use them to analyze systems under different conditions, and we can use them to derive measurable properties. For example, we cannot measure entropy, but entropy can be expressed in terms of measurable properties such as pressure, volume, and temperature, which are experimentally accessible. And we need the fundamental property relations to establish equilibrium and spontaneity. The example for spontaneity are Gibbs free energy and Helmholtz free energy. So we can see that when Gibbs free energy and Helmholtz free energy are greater than 0, a process can be spontaneous. The difference is they both express spontaneity under different conditions. The Gibbs free energy gives spontaneity at constant temperature and constant pressure, whereas Helmholtz free energy gives spontaneity at constant temperature and constant volume. To derive the fundamental property relations, we need to start from the first law of thermodynamics. So, according to the first law of thermodynamics, for a closed system, we can write the law as du, that is change in internal energy, is equal to the change in heat minus change in the work done. We can call this equation as equation 1. And from the second law, for a reversible process, heat is equal to temperature times the change in entropy, and the change in work is equal to pressure into the change in volume. When we substitute these two expressions into equation 1, so we can rewrite the equation 1 as du is equal to TdS minus P dV, and we are going to call it as equation 2, and this is the differential form of internal energy. To derive the differential form of enthalpy, so we are going to write the definition of enthalpy. So that is enthalpy H is equal to internal energy plus pressure volume. When we differentiate, we can write it as dH is equal to du plus P dV plus V dP, and this is going to be equation 3. So now when we substitute equation 2 in equation 3, we are going to get dH is equal to T ds minus P dV plus P dV plus V dP. And as we can see, we can cancel plus P dV and minus P dV, and therefore finally what we are going to get is dH is equal to T ds plus V dP. So this is the differential form of enthalpy. So to derive the differential form of Helmholtz free energy, again we are going to start with the equation of Helmholtz free energy, which is A is equal to U minus Ts. So when we differentiate this equation, we can write it as dA is equal to du minus T ds minus s dt, and this is equation 5. So now when we substitute equation 2 in equation 5, we can rewrite the equation as dA is equal to T ds minus P dV minus T ds minus s dt. So the plus TDS and minus TDS will get cancelled, and finally what we get is dA is equal to minus P dV minus S dt, and this is the differential form of Helmholtz free energy. To derive the differential form of Gibbs free energy, we can start with the definition of Gibbs free energy, which is G is equal to H minus Ts. So when we differentiate this equation, we get dG is equal to dH minus T ds minus S dt, and this is equation number 7. We are going to substitute enthalpy, substitute H in equation 7. So we can get dG is equal to T ds plus V dP minus T ds minus S dt. So we can cancel out plus TDS and minus TDS, and finally we get dG is equal to V dP minus S dt, and this is the differential form of Gibbs free energy.